Antiderivative. So a function, capital F, is how we usually note the antiderivative of the function f on the interval I is basically for f to be our antiderivative, capital F, the derivative of capital F of x has to equal lowercase f of x. Alright, so the derivative of capital F of x equals lowercase f of x. Right, and then the capital F of x is the antiderivative. So an example, if capital F of x is x squared, that's an antiderivative of 2x. Because if we take the derivative of capital F of x, we get 2x, which is the same as little f of x. But x squared is not the only antiderivative of 2x. There's actually infinitely many antiderivatives of 2x. Can anybody else come up with one? So basically, what you're asking yourself is, what has a derivative that's equal to 2x? Or what has a derivative equal to 2x? So we already established x squared is 1. Anybody come up with another expression that has a derivative that's equal to 2x? Guesses? Don't be shy. It's okay if you're wrong. Knock the dust off of those brains from Thanksgiving break. What else has a derivative that's equal to 2x? Yep.
X squared plus 1.
There you go. X squared plus 1. Right? Derivative of x squared is 2x. Derivative of 1 is 0. So that still has a derivative of 2x. So this would be an antiderivative of 2x. Anybody want to give us another one? X squared plus 10, right? We could do x squared, x squared minus 99. Right? It could be anything if we add or subtract a constant. So we don't want to write down, and we can't write down every possible antiderivative of 2x, but we can represent it using x squared plus c. Right? So we use capital C just to represent the constant. It could be any constant. Kind of like when we do like trig equations, you're solving those, you have to do the like plus 2 pi n or plus pi n to represent all the possibilities. Similar idea here. This represents all the different possibilities without having to write them all down. Now, up until now, we've started out with functions and found their derivatives. But if we're given a derivative to start, how do we find the original function? Well, the answer is to take the antiderivative. And this is something we'll kind of talk about a little bit more as we go on. But this is called a differential equation. All right, a differential equation is an equation that has a derivative in it. All right, so we're given the derivative. We want to find the original equation for y. Differential equation. So to do that, first thing we're going to do, and we'll do, again, more examples of this exactly later in the chapter, but we want to separate the variables. Here we have dy, dx. Well, we want the y stuff on one side, the x stuff on the other. So I'm going to multiply both sides by dx. And we get dy equals 2x dx. And then after these variables are separated, what we need to do is take the antiderivative, like I said up here. There's a symbol for the antiderivative. Just like there's a symbol to tell us when to take the square root, there's a symbol for the antiderivative. And it's called the integral. And the symbol looks kind of like a tall, skinny S. Integral. Right, so at this point with this problem, we would take the antiderivative of both sides. Right, so we're doing the antiderivative of both sides, so we can use that integral on both sides. And that integral just means take the antiderivative. You're asking yourself what has a derivative equal to what's inside the integral. So here we have antiderivative of 1 dy. So basically what we're asking ourselves is what has a derivative of 1 in terms of y. Right? So we've got a dy here, means it's in terms of y on this side. The dx means we're doing this in terms of x. So what has a derivative equal to 1? Because I want to know. Yeah, antiderivative of 1 in this case would be y. But we'd have to do the plus c to represent all the possible answers. Over here, we already talked about this, the antiderivative of 2x. Well, that's going to be x squared plus c. Now, these two c's are not necessarily the same, these two constants. So for this instance, I'm going to put like a 1 and a 2 here to represent that they could be different constants. All right, but then to solve for y, remember that's our goal here, is to solve this equation for y. I would subtract c from both sides, the c1. Well, if we take a constant minus a constant, we're just going to end up with some other constant. So in this case, I'm just going to leave it as plus c. And from here on out, in these types of problems, we don't have to worry about having a constant on both sides. Because all that's going to end up happening is we're going to subtract that one constant from this side to this side, and we're just going to end up with a plus c on the x side. So after this problem here, we don't have to do plus c1, plus c2. We're just going to have the plus c on the side with the x. All right, but we'll look at those a little bit more further down the line. So an indefinite integral, if we take the antiderivative of f of x dx, that's going to equal capital F of x plus c. Right? As long as what we talked about earlier was true. As long as the derivative of capital F of x equals lowercase f of x.